Okay, this is it. This is the last lecture about temperature, and this isn't really big ideas. This is some very small, specific stuff that deals with temperatures. You need to take notes as you're watching this video, and I'm very, very clear about what's important. Definitely any word that is red in bold, that's a vocabulary term that needs to go in your notebook so that you can look it up when we get to the test, which is coming up very shortly. First of all, we're going to do another virtual lab here, and this is something I did in the classroom, and I'm going to show you the results. Normally we would do this together, but not this year. So here's what we have. We have some white sand and some black sand. They're both sand though. Remember, so they're the same material, and they should heat up the same way because they're the same thing. I put them, first of all, I took their starting temperature. Both started off the same, about 78 degrees. Then I turned the lamp on, let the lamp shine on both of them equally for about the same amount of time. And I noticed what happened. The black sand heated up to 87 degrees, which means it went up 12 degrees. The white sand only got up to 79, meaning it only rose 4 degrees. So we've got two things of the same material, getting the same amount of sunlight, and yet their temperatures change differently. So there's another key idea or concept that makes a difference in terms of what determines something's final temperature. The concept that we're looking at here is called albedo. Albedo is the idea that dark colored objects absorb energy and therefore have higher temperatures than light objects that tend to reflect sunlight. It works like this. A high albedo object has about 80% of its sunlight will just hit it and bounce off because light colors bounce off sunlight. But a darker object has a low albedo. It might only reflect 10% of its sunlight. So if you are absorbing 90% of the sunlight that's hitting you, you're getting more energy, you're going to have more friction, you're going to have a higher temperature. But a lighter object isn't going to soak up the energy, and without gaining energy, your temperature doesn't go up much. This is why in the wintertime you tend to wear dark clothing because it's cold outside and you want to be warmer. So you wear dark clothing that will soak up energy and therefore increase your temperature. On the other hand, in the summertime, you wear lighter colors because lighter colors are going to reflect sunlight. It's already warm enough in the summertime. You don't need to get more energy. As a matter of fact, you want to do the opposite. You don't want to get hotter because it's already hot. So you wear light colored objects that are going to reflect sunlight and help to keep your temperatures a little bit lower. This is why black cars are always going to be hotter than white cars that are sitting under the same sunlight because the black's going to absorb more energy and get hotter than the white. So what does that have to do with our planet? Our planet doesn't change its wardrobe from summer to winter. How does this affect temperatures on the planet? Well, think about things that are white, like clouds. Clouds reflect almost all of the sunlight that hits them. And you know this to be true. This is why when you're outside and a cloud comes overhead and blocks the sun, you can feel the difference in the temperatures. In this area right here, the temperatures are going to be significantly cooler because the sunlight that's hitting the cloud just bounces off. Because clouds are white, and white things reflect most of the energy that hits them. Well, what else is white on the planet? Snow and ice. So if there's more snow and ice on the planet, it's going to reflect more sunlight. And if you're reflecting more sunlight instead of soaking it up, your temperatures are going to be lower. This is another reason why Antarctica or the South Pole is so cold. So right here at the South Pole, notice you're surrounded by ice. And even if you do get some sunlight, and you don't get a lot at the South Pole, the sunlight you do get, 90% of it is bounced back off in outer space. So you can't help but be cold at the South Pole because the sunlight you get is being reflected by that white ice that has a high albedo. Now what about dark surfaces? So let's imagine that the snow and the ice melts and you've got ground underneath, or you've got the ocean underneath, which are both very dark in color. Well, then the solar energy gets absorbed instead of reflected. Well, if you absorb solar energy, your temperatures are going to go up. So this is what's happening on our planet right now. Because most of the ice reflects sunlight, that helps deflect some of the sun's energy, helps keep the Earth's temperature a little bit lower. But as the polar ice caps melt, what we see underneath is more water, and water is dark, so it's going to absorb more sunlight and the temperatures are going to go up. So here's what you can see on this slide, that 90% of all of the sunlight that hits snow and ice gets bounced off in outer space. So it's not used to change our temperature. But when you talk about the ocean, 94% of the sun's energy is basically going to be soaked up by the ocean. And the more energy you soak up because you're a darker color, the higher your temperature is going to get. And this is what's happening on our planet right now. So Greenland's a case study for us, because Greenland is mostly covered by snow and ice. So it reflects most of the sunlight that hits it, bounces it off back out into outer space, and our temperatures don't go up. But what's happening in Greenland is that a fair amount of the snow and ice is melting. You can see from 1992 to 2007 how much smaller the ice cap is getting. Well, what's underneath there is dirt and ground, and that stuff actually soaks up sunlight and gets warmer. That means our planet is getting warmer as we lose more snow and ice. The snow and ice has a high albedo that will bounce sunlight back into the outer space. So if we take the lid off the planet, if we take this ice off the top of our planet and we start soaking up more sunlight, we are going to get warmer. And as we get warmer, more snow and ice melts, which means we soak up more and more energy and our temperatures go up. So this is kind of like a cycle. And as we get warmer, more ice melts and we keep on getting warmer. This is the whole idea behind the concept of global warming. The planet is getting hotter, and this is one of the reasons why. So to define what global warming is, it's a simple term. It's just the Earth getting hotter, which the Earth is. We know this to be true. We can measure the temperatures of the Earth from year to year, and we can see that, hey, it's getting hotter. So what's the big debate with global warming if it's not about the temperatures? Well, there's another little part to this that we have to talk about, and this is called the greenhouse effect, and this is another virtual lab. Here's what I did. I took 2 Gatorade bottles, and you'll notice I put a cap on one and I left the other one open. Then I shined a light on there for a certain amount of time, and I recorded how much the temperature changed. Well, as it turns out, this one here got hotter. This one here did not nearly get as hot, because what happened was, as the air got hot, it expanded and it came out the top. And when it came out the top, it took energy with it. But in this one, the air couldn't get out. So instead, it just kind of bounces around inside there as it gets more energy, causing more friction and get hotter and hotter. Well, this is very similar to the greenhouse effect. The greenhouse effect is basically putting a cap on our planet that traps heat. Well, it's not a Gatorade cap. So what is it? Well, here's what's happening. You know we have an atmosphere. And when sunlight comes through the atmosphere, some of it hits the Earth and gets soaked up by the Earth, and the Earth gets hotter. Some sunlight bounces off the Earth and goes right back out to outer space. But some heat energy actually kind of bounces around and gets trapped by our atmosphere, by those gases in the atmosphere. That's what the greenhouse effect is. It's the atmosphere, the gases in the atmosphere trapping sunlight, trapping heat. Now, if we didn't have an atmosphere, a lot more of our sunlight would bounce off in outer space and we'd be colder. If we had a thicker atmosphere, well, then we would trap more sunlight and we would be hotter. And this has happened in our solar system. Venus has too much atmosphere. It has what's called runaway greenhouse effect. The greenhouse layer of gases is just too thick, and the sunlight that gets in there just gets trapped and bounces around, and Venus is impossibly hot. Can't live on Venus. It's too hot, traps too much energy. This would be like wearing a blanket on a hot summer day. That's what Venus is like. It's got a big, thick blanket around it. On the other hand, Mars has lost most of its atmosphere. So Mars basically doesn't have a blanket. So when sunlight hits Mars, there's nothing to trap it, and it just bounces off in outer space. So basically you freeze to death on Mars, especially at night when the sun's not shining. But On Venus, you end up cooking yourself to death. And this is because of the greenhouse effect. Too much or too little can be very, very bad. It makes it where it's not livable. Luckily, we're kind of what's called a Goldilocks planet, where our greenhouse effect is just right for us to support life. It's not too hot, but it's not too cold. That blanket of gases around the planet is just right. So, is the greenhouse effect good or bad? It's definitely good. We need the greenhouse effect. If we didn't have the greenhouse effect, we would freeze to death every time the sun went down. And we would fry every time the sun came up. We need something to help kind of regulate our temperatures and trap just the right amount of heat to make it livable. So too much greenhouse means the planet holds too much energy. Too little greenhouse means it doesn't hold enough energy. You get too cold or you get too hot. The major number one gas in our atmosphere that traps heat, the number one greenhouse gas, is carbon dioxide. Now, carbon dioxide is natural. It's not a man-made thing, although we do make it when it gets released when we burn fossil fuels. But the greenhouse effect is natural. Starting off, originally the greenhouse effect is natural. So this carbon dioxide, though, that we put into the atmosphere when we burn fuels in our car is making that blanket thicker on our planet, which means we're trapping more heat, which means that explains why the temperatures are going up. So what we're doing is putting more of those greenhouse gases in the atmosphere, and we're trapping more heat. So what's the big argument about global warming? You hear about it a lot, about the climate accords, and the politicians argue about global warming and climate change. Now, keep this in mind. The argument with global warming is not if the planet is getting hotter. We know it is. We know temperatures are on the rise. The argument is, are we causing it to happen faster because of all those extra greenhouse gases, all that extra carbon dioxide that we put in the atmosphere? We know the planet has gotten hotter and colder in periods of time in history. We've had ice ages and we've gone hot, and then we've gone cold again and we've gone hot. The planet's temperatures go back and forth. That is natural. The argument is, are we causing it to happen unnaturally? And if we are, what can we do to stop it or slow it down? And that's where the argument comes in. Some people think that, hey, we're burning too many fossil fuels. If we cut down burning fossil fuels, we will slow down this global climate change. Other people, on the other hand, are saying, nah, you know what? People are too small. There's, you can burn all the gasoline in the world, and it's not really making that much difference. This is going to happen anyway. So that's the debate about global warming. Now, whether or not really it's happening or not, that we can measure temperatures from year to year. We know the Earth is getting hotter. The question is, are we causing it to get hotter? And if we are, what can we do to stop it? Now, some more temperature data here. Let's take a look at something else. So I went outside and I painted a white square on the concrete outside my classroom. And a nice sunny day, it was 109 degrees. Soaks up a lot of energy. It's Georgia. This was in August, actually. It's hot. I also painted a black square and it was 115 degrees, which we just saw. That makes sense, right? The darker color is going to soak up more sunlight and become warmer, like the dark sand versus the white sand. So darker things soak up more energy and get hotter. So the nice dark grass was only 86 degrees. So even though the grass was a nice dark color, its temperature was significantly lower than the lighter colored white concrete. So this begs the question, why? Why is the grass, even though it's dark, why is it cooler than the other stuff? Well, that's what we're going to look at now, the effect of plants on temperature. You all know about photosynthesis. You know that plants take sunlight and they use sunlight to make their food. Okay, that makes sense. But if a plant is using sunlight to make food, the sunlight can't be used to raise temperatures. So it's got to do one or the other. Think about it like this. Imagine if I gave you a dollar bill. I said you can spend it or save it. You can either save it or you can spend it, but you can't do both with the same dollar bill. So it's one or the other deal. Well, think about the dollar bill like sunlight. Well, what can a plant do? I mean, it's got one of two things. It can either make food for itself, or it can raise its temperature. Well, out there in the real world, energy from the sun, we know if it hits something, can be used to raise temperature, unless you're a plant. A plant has this option. A plant can take sunlight and use it to make food. It can do photosynthesis. Now, a parking lot can't photosynthesize. So a parking lot, when it gets sunlight, gets hotter. Definitely, because that's the only choice. It can't photosynthesis. Now, a plant, on the other hand, plants love making food out of sunlight. They love photosynthesizing. That's why they have big leaves and all those chloroplasts in there. So a plant is built to take sunlight and turn it into food, which means it's not going to get hot. Plants do this with sunlight, which means they cannot raise temperatures. If you go outside, even on the hottest of summer days, and touch a leaf, touch the grass, it's going to feel cooler to you, because the energy that hits those plants is not being used to get hotter, it's being used to make food. So all the sun's energy that hits a parking lot, can the parking lot photosynthesize and make food? No. So what happens is a parking lot, when it gets hit with sunlight, all of the sunlight ends up making that parking lot hotter. It's got no choice. That's the only, remember, there's only two choices. You can use it to make food or get hotter. A plant, on the other hand, plants are super efficient at taking sunlight and making food, because that's what they're doing. Plants want to photosynthesize. So almost 100% of the energy from the sun that hits a plant is being used for photosynthesis, which means it can't be used to raise temperature, which means the plants don't get hot.
So here I am at the former Super Target on Holcomb Bridge Road. And you may not know this, but up until not too many years ago, this entire area was a forest. It was nothing but trees. Well, they came and they cut down all of the trees, and they paved this parking lot, and they built the building back there. So what does that have to do with temperatures? Well, on a nice sunny day like today, all of the sunlight hits the nice dark parking lot, hits the metal building, and all of that sunlight gets soaked up, which means the temperatures go pretty high. The temperature of this parking lot is about 120 degrees. Now, what would have been different had they left the forest here? Trees will soak up sunlight, but they use the sunlight for photosynthesis to make their food. Well, if the sun's energy is being used to make food or photosynthesize, that energy then cannot be used to make particles move faster, create more friction, and raise temperatures. So we know this, that plants help keep the temperatures cooler, because the plants will use the sunlight for photosynthesis. This parking lot can't do that, so you build parking lots, you build buildings, and the temperatures go up. Roswell is now hotter than it was before they built this Super Target. So the more trees we cut down, and the more parking lots, and the more roads, and the more buildings we make, the hotter an area gets. That's a phenomenon known as the urban heat island, or the fact that cities are hotter than the countryside, because we take away the plants and we replace them with materials that just get hot as they soak up the sunlight. So once again, this leads to the phenomena known as the urban heat island, or the fact that cities are hotter than the countryside because there are so many fewer plants to soak up the sunlight. Alright, so now I've gone just a few miles away from that previous location, and I'm on the Big Creek Greenway, which is a large area of undeveloped land here that runs from Forsyth County all the way through Roswell and Alpharetta. And as you can see behind me, there is no development here. There is no roads. They've left the trees and all of the plants in place. And when you take the temperature reading here, the temperature here is about 83 degrees. And that's because all of the sunlight is hitting those trees, it's hitting these plants, and the plants take that sunlight and soak it up through their leaves, and they use that energy to make their food through the process of photosynthesis. Well, a road and a parking lot can't do that, so when sunlight hits roads and parking lots, the temperature goes up. But if we leave plants and trees in place, It dramatically lowers the temperature of an area because the sunlight is used to make food for the plants and the trees, and therefore it cannot be used to make particles move faster, increase friction, and raise temperatures.
Now, there's another way in which plants help moderate temperatures, and that's this process called transpiration. Transpiration is just water that plants release into the air. And you get this, plants, they soak up water through their leaves, and they have little pores that they spit water up into the air. So if you have a lot of plants, you tend to have more water in the air. And we know that water doesn't get really hot and really cold that easily. So a lot more plants help to keep temperatures more stable because of transpiration and the amount of water that's in the air. This next concept called the urban heat island effect. This is a real simple idea that cities are hotter than the countryside. If you live in a city, you're going to have higher temperatures than you live out in the country. Here's the thermal image of Boston. You can see, you know what the reds are. The reds over here are the hot temperatures. And if you look at this, you can see that's where all the city is. But you look out here where it seems to be a little bit greener, like out in the countryside, and you go up to that part of the map, hey, it's colder out there. This is a very true, a very real thing that cities are hotter than the countryside. One other thing you'll notice is, look at the ocean. The ocean, the water tends to be a little bit cooler because remember, oceans don't get as hot or as cold. Here's Paris. And you'll notice, look, it's hottest right there in the center of the city where there's going to be the most buildings. As you go away from the city, you can see the temperatures go down. Cities are hotter than the countryside around them. You can see it here. Here was some snowfall in Minnesota. You can see this is all snow out here. And yet right in here, there's a little spot where there isn't any snow because it was warmer there. It wasn't warm enough for snow. That's the city of Minneapolis. Because the cities are warmer, the snow there melted and it doesn't look like there's snow on the ground. And you can actually see that on this satellite map. Here we are, city of Atlanta. Here we are, 65 in Atlanta. You'll notice all of these other temperatures around the city are all cooler than the downtown city because the cities are hotter than the countryside around them. But the question is why? What's the difference? Well, what's different about the suburbs versus the city? First of all, we're going to look at an infographic about how Atlanta has changed in the past 30 years. Now, on this graphic, green represents areas that are at least 50% covered with trees, and red and black stuff means urban areas like, buildings and roads and parking lots. And you can see in 1973, for a lot of the Atlanta area was covered in trees. There was still, there's our downtown area. Here's our area down near the airport. This is kind of getting up towards Marietta, and this is going out like, towards Gwinnett, kind of like Doraville out that way. So you can see a lot of trees in Atlanta in 1973. By 2003, however, you see a lot more of the trees have been cut down because we built more roads, parking lots, houses, buildings, shopping centers. So there's so many less trees in 2003 than there was in 1973. So what do you think the difference was with temperatures? Well, with fewer plants and trees, the temperatures are going to change because plants and trees help keep temperatures lower. Here's a graphic of the temperatures. Notice you had a little spiky little hot area here by the airport and by downtown. But by 2003, look how much hotter we're looking at here. Because so many more of the trees have been cut down that the temperatures are going to get higher and higher and higher. Here's New York City. And you'll notice this blue area here. This is the water around New York City, which, it's not going to get really hot. This area here is Manhattan. It's pretty warm. A lot of buildings over here are getting pretty warm. But notice there seems to be a blue triangle, a cool triangle in the middle of New York City. Well, why is that area so much cooler than all the other area around it? Because that's Central Park. And you can see it here. There's Central Park, and it's an area filled with green plants. And everywhere else around it is all buildings. So this area stays a lot cooler than this area over here. Central Park is a big place for people in New York City who don't have air conditioning to go in the summertime because it's going to be a few degrees cooler than sitting in their city block where it's just filled with buildings and roads and stores, where Central Park is going to remain a little bit cooler, especially because it has a nice big lake in the middle, which will not get as hot or as cold. So I know, why should you care? And one of my big incentives in this class to you is to try to show you why should you care about this stuff, because this will impact you at some point in your life. The answer is money. We all care about money. You have to run your air conditioner, and then you have to pay your power bill based on how much you have to turn this thing on. And your air conditioner and your heater sometimes is the most or the biggest energy drain in your house. You have to run the air conditioner and you got to pay a bigger power bill. Our most expensive power bills are going to be in the summertime because our air conditioner takes so much electricity to run. And everybody has to run their air conditioner in the summer, but the question becomes how much. The less you run your air conditioner, the lower your power bill. It saves you money. The less we run our air conditioner, the less all of us have to run our air conditioner, and we all save money. It helps keeps the temperatures of the cities down. So we don't want our cities to be extra hot because it's expensive to live in an extra hot city. So what can we do? What can we do to combat this urban heat island, to make our cities not get so hot? Well, the first and the easiest thing is quit cutting down all the trees. We can plant as many trees as possible. Now, that can be a challenge because we can't go back and tear down Kroger. We can't tear down Centennial's campus. We can't plant trees in the middle of our parking lot, but we can be a little more careful about how we take trees out in the first place. Think about a parking lot like this. You can fit in some trees in there. There's a fair amount of green trees in this parking lot, and that's going to help keep the temperatures a little bit lower than if it was just a parking lot. These two parking lots here. This parking lot over here is going to be cooler than this one. This one's going to be hot because it's all blacktop, and there's no green plants to soak up some of the sun's energy and use that energy to make food. Nowadays, most places won't let you build just a wide open parking lot like this. I'm like, no, we know that's bad for the cities. You're going to be required to put in some plants someplace in your parking lot to try to help keep temperatures down. Another neat thing you can do is make what's called a green roof. A green roof is simply when you put plants on the top of buildings. And what good does that do you? Well, the green plants soak up sunlight and use it to make food via photosynthesis, which means the plants don't get hotter, which if the plants don't get hotter, the city stays cooler. If this were just a regular rooftop of a building, it would be sitting in the sunlight and it would be just getting hotter and make the city hotter. But plants on top of roofs help to keep temperatures down. This is an example of one in Singapore. Here's one in Fukuoka, Japan. You can see a lot of big trees on the side of this building, planted on the side and or top. This is going to help keep this city a little bit cooler than if this was just a metal roof building. Now you can see most of Fukuoka, Japan looks like this. There isn't any green at all, so all of the sunlight that hits an area right in there is just soaked up by those buildings, and those buildings get hotter. So the city gets hotter. So in a place like this, they're trying to be more proactive in putting in more plants on top of buildings so that they help keep the temperatures down. Here's Edinburgh, Scotland. You can see there's some trees and some grass. It doesn't take much, and if everybody does a little bit, it collectively can make the city cooler, and even just a few degrees makes a big difference. This is Berlin, Germany. Notice it doesn't have to be pretty plants, doesn't have to be fancy plants, doesn't even have to be trees. Anything that is green that will photosynthesize and take sunlight and use it for photosynthesis as opposed to raising temperatures will help keep temperatures lower. Here's in Hong Kong. You see on top of this big, huge building here, all these plants and trees that are going to photosynthesize. This is what most of Hong Kong looks like. you can see it's a lot of brick buildings that are just going to soak up sunlight and get hotter. So if you can put more plants on top of these buildings, you're going to help lower the temperatures in the city. Here's another example. You got a big tree up there. Big tree, lots of leaves, soaks up lots of sunlight. Or you can have just things that look like basically ground cover, like little mossy plants. Anything green will soak up sunlight and help keep temperatures down. Now here's the thermal image between a green and a conventional roof. Notice this is a conventional roof. There's no plants there. And this one has plants. Look at the temperature difference between the two of them. This one over here is significantly hotter, and this one is icy cool. The plants make a huge difference. Any place you can stick some extra plants will help. Think about railways. Most of the time, in between the rails, you got rocks, and rocks just sit there and soak up the sunlight and get hotter. But if you just plant some grass there, any green plants are going to help soak up sunlight and photosynthesize, which will then mean there's less energy to make temperatures hotter in cities. Now we can also change the color or the materials that we use in the city, because remember, the color makes a big difference. Here's a shopping mall that they did a little experiment on in Florida, and they painted one side darker colors and they painted the other side a lighter color. And you can see over here how much darker it looks than over here, because the lighter color reflects more sunlight. Now this is in Florida where it's already pretty hot and they get a lot of sunlight. So this side of the shopping center will theoretically have to use less air conditioning because more of the sunlight is being reflected. Over here, because it's darker materials, the sunlight's going to be absorbed. You're going to get hotter. You're going to have to run your air conditioner more. If you think about places that are notoriously hot, like I went to Dubai a couple years ago, it's in the desert. I mean, it's in the Middle East, it's hot. Almost every single building there was painted a lighter color because when the sunlight hits the building, we want it to bounce off. It's already so hot there, we don't want our buildings to soak up any more sunlight than we have to. You would never paint a black building in Dubai. It would just be impossibly hot, and you have to run your air conditioner all the time to keep it cool. Now, you can also make what's called a cool roof. A cool roof is just simply putting lighter colored materials on top that will reflect sunlight. With older buildings in older cities like Chicago and New York, they make this white fabric that you then basically just shrink wrap on the top of a building. What does that do for you? Well, with a cool roof that is white, most of the sunlight gets reflected. If you have a traditional tar roof, which is black, it soaks up a lot of sunlight and then gets hotter. So a cool roof is merely just a roof that is painted or covered in lighter color material that will reflect more sunlight. Here you can see the difference between a black roof or a traditional roof and a cool roof. These buildings were built at the same time. The cool roof just had the extra material put on top of it that's now white. Notice the difference here. Here's an office building that has a cool roof, and there's the blacktop, the parking lot. Notice the difference in the temperatures between the two. This works. And the more buildings that put on these cool roofs means the lower the temperature of the city and the less we have to use our air conditioner. We all save money and we save resources. You can also do this with parking lots. They've started to make asphalt parking lots not be black anymore. You make a lighter colored parking lot, it's going to be cooler than the black asphalt. Same concept. The dark pavement only reflects about 10% of the sunlight, which means it soaks up 90%, gets hot. If you have what's called cool pavement, it's going to reflect up to about 40%. So it's not soaking up as much energy, it's going to stay cooler. Here you can see a thermal image where they made a road where this is the cool concrete and this is the regular asphalt over here, and you look at the temperature. This one's hot, Sorry. And this one's significantly cooler. And you can see it hot here because it's the regular dark asphalt, and this is cooler because it's the cool concrete. If you can, let's use less asphalt, period. If we didn't use asphalt and concrete, just use natural like gravel and things like that, that can help keep temperatures down because these things don't soak up as much sunlight. They're not as dark. You can do something like this in parking lots. A great advantage here is that now we've got some grass in the parking lots, and the grass is going to soak up the sunlight and use it to photosynthesize and therefore not get as hot. Now, there's some disadvantages to this. You can't use this someplace where it gets used every single day and gets a lot of traffic because all the cars would drive on the grass, and if there's too many cars parked over top of the grass is in the shade, grass won't grow, kind of defeats the purpose. But a place where you don't use the parking lot every day, this would be a good option, especially someplace like a church where the parking lot is primarily only used on Sundays. Well, the rest of the week, the grass can get sunlight and grow, but the grass soaks up sunlight and doesn't get hot. So my area, my city doesn't get as hot. In places where they get a lot of sunlight, you'll notice kind of wildly bright colored houses, like in Florida. These are all in Florida. They get a lot of sunlight. It's warm enough there, they don't want to soak up any more sunlight and make their house hotter where they have to run their air conditioner more. So they paint their houses really light pastel colors. And what happens is it reflects the sunlight and the houses stay cooler. This is at Aruba near the equator where it's the same deal. Have a lot of direct sunlight. You don't want your house to soak up that sunlight, so you painted a lighter pastel color that will reflect the light as opposed to soak it up. Same thing in Puerto Rico, a lot of lighter, brighter colors that will reflect sunlight as opposed to soak it up. In Greece, every house was whitewashed because it was already so warm there. And this is areas where you didn't necessarily even have air conditioning. So forget running your air conditioning in the first place. You needed to keep your house as cool as possible, so you painted it white and it would reflect sunlight as opposed to soak it up. Now we've got a bunch of new vocabulary here. Here's a summary. All of these should be in your notes, and I would label a page in your notes, temperature notes, final temperature notes, whatever. But these are the vocabulary terms outlined for you. These are key concepts that you should understand after watching this presentation. Now you can go back a few seconds. You can hit the back button on YouTube and go back and pause it and get those vocabulary terms in your notebook, and you should be able to answer these questions. I would encourage you to write these questions actually in your notebook and write the answers underneath them. So that's the end. If you have any questions about whether or not you understood something on this video, you can ask at any time.